Welcome to Math with Professor V. In this video, we're going to learn all about how to graph roses in polar coordinates. I have 5 excellent examples selected for you that we're going to work through together. And then also, in case you're a Calculus 2 student, after graphing each of these examples, we're going to find the area inside one of the petals and the entire graph. So this video is going to be perfect for you, whether you're in pre-calc and you're just learning polar coordinates and graphing, or maybe even trig, or whether you're in calculus and you need to find polar areas. This will help you master this unit. So you know you're dealing with the graph of what we call a rose if the equation has the following form. Either r equals a cosine and then there's some constant n times theta, or r equals a sine n theta. A is always positive. Okay, now if n is even, then you have 2n petals. You have double that number of petals. And then if n is odd, you have exactly n petals. So here's some examples. And I mean, it doesn't really look like a rose, but this is what we call a rose, okay? So you would have a rose with 3 petals if there's a 3 in front of the theta, because 3 is odd. So that tells you, boom, you got exactly 3 petals, 1, 2, 3. Now, where exactly they're oriented depends on whether you have sine theta or cosine theta. So we'll work on putting that together. And then notice here, n is 2, which is an even number. So then you have 2 times 2 petals, or 4 petals, and your rose would look something like this, okay? So we're going to work through, like I said, 5 examples. The most common requests were to do odd number of petals, so that's what I'm focusing on, but I also do have some evens, and we're going to find areas as well, okay? Also, the request came in that they get no calculator in their class, so I'm going to do it that way as well. All right, graph each of the following. And then this is the extra part. So if you're a calculus student, pay attention to this. We're going to find the area enclosed by 1 petal and the entire graph. If you're not in calculus yet, just ignore that second part of the directions, and I'll tell you when you can skip in the video. Okay, so here we go. We have r equals 2 sine 3 theta. A in this case is 3, right? Or n in this case is 3, excuse me. So this tells me, since that's an odd number, I have 3 petals. Now, the most important thing you need to figure out is how long or how often, right, does it take for each petal to get traced out? And basically the way you answer that question is you set the polar equation r, so 2 sine 3 theta equal to 0. Because you want to know how long it takes for the graph r to start at the origin and then return to the origin, Every time it comes back to the origin, a petal has been traced out. So that's why we set it back to 0, because that would indicate we're at the origin. Now we're going to solve this trig equation, and you have to be careful because of that 3 in front of the theta. So dividing by 2, this is sine 3 theta equals 0. And then leave that argument alone. Leave the 3 in front of the theta, and you ask yourself, when is sine equal to 0? Sine is 0 at 0, pi, 2 pi, 3 pi, etc. So sine is 0 at 0 plus pi times k, where k is an integer. Hopefully you've seen this notation before. We can actually abbreviate k as an integer by saying k is an element of the set of integers, that z right there. So I'm going to repeat this again. Sine is 0 at 0 plus any integer multiple of pi. There's infinitely many places. Okay, so that's when 3 theta equals 0 plus pi k, but what about theta? I'm going to divide by 3. I don't need to keep this 0 here. That's pointless. So theta equals pi over 3 times k. So this tells me, boom, right here, every pi over 3, a petal gets traced out. And I have 3 petals. So if it takes pi over 3 for a petal to get traced out, times 3, after pi, the entire graph should be traced out. So you don't need to make a table now from 0 to 2 pi, just 0 to pi should do it. Now for this first one, I'm going to make a very detailed table, and then I'm going to show you some things that you can kind of skip to save time, okay? So here we go. Let's make our table. Theta, and then r, which is 2 sine 3 theta. And I want to point out some things that you need to keep in mind when you're graphing here, okay? And you know what? Let's scoot this guy down so you can see. So typically on your polar graphs, right? Like here's 0, this is pi over 2. This is one of my favorite ones because it has just enough but not too much. When they're too busy, it kind of drives me crazy. So right here, this is pi over 6, pi over 4, pi over 3. This would be 2 pi over 3, 3 pi over 4, and 5 pi over 6. Now, if you only plug in these values into your table, you typically don't get enough to draw a nice rows because of the 3 in front of the theta. It's kind of scaling everything up. So you need to be a little more detailed. How detailed? We're going to do this one by exploration together, and then we'll come up with a pattern, okay? So just to have a little more going on, I'm going to add pi over 12, believe it or not. Yeah, half of pi over 6, okay? And then like from there, these are all pretty much evenly spaced. So let me add one more in here so we're not missing too much. So if I'm cutting that in half, this is 4 pi over 12. This would be 5 pi over 12, 6 pi over 12. Yay, fractions. Okay, 5 pi over 12. Boom, 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 boom. And then 7 pi over 12. Boom, 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 boom. And then this would be 11 pi over 12. Okay. And then maybe sometimes that's not enough, but this will be plenty for our purposes. So here we go. I'm going to substitute all these in. So we've got 0, pi over 12, pi over 6, pi over 4, pi over 3, 5 pi over 12, pi over 2. This is probably more than you actually need, okay? But for the first one, I wanted to do like a really thorough job, and then we'll make some observations so we can plug in less values into the table in the future, okay? So this one's just first for you guys to get an idea what's going on. Okay, and you're substituting in these values for theta. Okay, so 2 times sine of 3 times 0, that's just 0. Now the next one, like pi over 12, that's 2 times sine of 3 times pi over 12, right? So then that's 2 times sine of pi over 4. Pi over 4 is our 45-degree reference angle. Sine of pi over 4 is rad 2 over 2. So this is 2 times rad 2 over 2, which is rad 2. Okay. It's helpful. Just keep this in mind moving forward in your math career. Rad 2 is about 1.4. And rad 3 is about 1.7. Okay? Especially like if you're not getting a calculator. Okay, pi over 6. I'm not going to keep writing it out like this. Hopefully you guys understand how to substitute them in. So pi over 6 in for theta, that's 3 times pi over 6, so pi over 2. Sine at pi over 2 is 1, so 2 times 1, this is 2. And then let's keep going. Pi over 4, 3 pi over 4. Sine at 3 pi over 4 is rad 2 over 2, so this is 2 times rad 2 over 2, which is rad 2 again. And then pi over 3. 2 times sine of 3 times pi over 3, that's going to be pi. Sine of pi is 0. Boom. Are you surprised? You shouldn't be, because it took from 0 back to pi over 3 to get one of the petals. We can fill in the rest of the table, or if you're just too excited like me, let's graph one of the little petals now, okay? So 0, we have 0. Pi over 12 is rad 2. Okay, so here's the pi over 12 line. Plot the radius at about 1.4. So here's 1, and then like 0.4, maybe it would be around here. And then pi over 6, here's the pi over 6 line. Radius is 2 right there. Pi over 4, it's rad 2, and then back to 0. Now keep in mind, this petal should live between 0 and pi over 3. So don't get carried away. Don't start drawing it all chunky over here. If you don't think you can hold yourself accountable, you know, here's pi over 3. Here's 0. The petal needs to stay inside there. You're like, I got it, Professor V. There we go. See that? See, don't let any of this spill over. That would be a no-no. Okay, beautiful. As you can see, the most interesting parts of the petal are where it's at the origin and when it's fully at the max length of 2. And notice here's 0 pi over 3. It hit the max length halfway between. That is no coincidence. We're going to use this to our advantage momentarily. Okay, let's keep filling in the table. Remember, we have 3 petals total. So 5 pi over 12, that's going to be 2 times sine of 15 pi over 12. Yes, that reduces to 5 pi over 4. So then we're in quadrant 3. So sine is negative rad 2 over 2. So then this is negative rad 2. At pi over 2, this is 2 times sine of 3 pi over 2, so 2 times negative 1, which would be negative 2. 7 pi over 12, this would give us negative rad 2. And then at 2 pi over 3, we're back to 0. No surprise. And then I'll just give you the rest of the values. 3 pi over 4, you should get rad 2. 5 pi over 6, 2, rad 2, and 0. So there's all 3 petals. Let's graph them now. So 5 pi over 12, negative rad 2. Don't let that scare you. So here's 5 pi over 12. I'm going to keep drawing it all the way into quadrant 3 since the radius was negative there. When you have a negative radius, that means you draw that point in the opposite direction. So here's 5 pi over 12. Negative rad 2, I'm going to go this way, 1.4. 1 and a wee bit more. Like that. And then pi over 2, negative 2. So here's pi over 2, but we're going this way, negative 2 down there. Very good. Look at you guys. Doing great. And then 7 pi over 12 is negative rad 2. So here's 7 pi over 12. It's going to go the opposite way. Negative 1.4. And then we're back to 0. Okay? So just keep it in here and you're good to go. So this petal's done. Love it. Petal 1, petal 2, and then petal 3. 3 pi over 4 is rad 2. So here's 3 pi over 4. Rad 2 is going to be about there. Okay. 5 pi over 6 is 2. 11 pi over 12 is rad 2. And then we're back to 0. Fabulous. There's my 3 petals, okay? I know, it doesn't really look like a rose. Again, notice these points here where it's at the max length when the radius actually equals 2 happen at pi over 6, pi over 2, and 5 pi over 6. So here's the thing. A petal gets traced out every pi over 3, right? 0 to pi over 3, add another pi over 3, add another pi over 3. Halfway between is where it hits the max length. So I'm not gonna, in the following examples, I'm not gonna do all these extra little bits. If you want to have more values for your petals, go for it. But really where it's at its max and the origin is what's most important. Good? Here's the 3rd petal. Okay. Now, if you're a calculus student, you'll be asked to find the area enclosed by 1 petal. So let's do that. If you are like in trig or pre-calc, then you don't need to worry about this just yet. So you can just skip on to the next example, okay? So to find the area enclosed by just 1 petal, that means we just want the area like of this portion here. I would take the easiest limits of integration for the petals. So 0 to pi over 3 would be my choice, right? You could go pi over 3 to 2 pi over 3, but I would rather have 0 as one of my limits of integration. So if you need to review polar areas, I'll link a video here, but the area is going to be 1/2 integral 0 to pi over 3 r squared d theta, and r is 2 sine 3 theta squared d theta. Good? And then from here, let's just clean up. So this is what? 1/2. 2 squared is going to be 4. Let me take it out of the integral. 0 to pi over 3 sine squared 3 theta d theta. Then I'm going to have a 2, 0 to pi over 3. How do we take the antiderivative of sine squared 3 theta? We don't. We replace it with 1/2 times 1 minus cosine. Be careful, be careful. You double that angle, so it becomes 6 theta d theta. And then, ooh, this is nice. This 2 and the 1/2 cancel. So now we're ready to take our antiderivative. However, I am out of space, so bear with. And then we're going to have antiderivative of 1 is theta. Antiderivative of negative cosine 6 theta would be negative 1 over 6 sine 6 theta. And that's evaluated from 0 to pi over 3. And then from here, we'll just get pi over 3 minus 1/6 times sine of 2 pi is 0. Minus, if I plug in 0 for the lower limit, everything's 0. So this is pi over 3. So the area enclosed by one petal is pi over 3. Now, what if they asked for the entire graph or the entire rows, right? Okay, you have to be careful. This is a dangerous moment. If you look at the entire graph, some students kind of get a little too excited and they go, I'm just going to integrate from 0 to 2 pi. That would be wrong. You guys, how long did it take to trace out this entire graph? It didn't take 0 to 2 pi. It took 0 to pi. So if you integrated from 0 to 2 pi, you would not get the correct answer. I think a safer, easier way of finding the area enclosed by the entire graph is just find one petal. And then you go, well, there's 3 petals. So the entire graph would be 3 times that amount, 3 times pi over 3, so pi. Okay? If you desperately want to just integrate it, then you would have to make sure that you have the correct limits of integration that it takes to trace out the entire graph, which in this case are just from 0 to pi. And then you would have r, which is 2 sine 3 theta squared d theta. Does that make sense? I just feel like that's a little more dangerous because you have to really have your wits about you and make sure that your limits of integration are exactly how long it takes for the entire graph to get traced out. It's easier to just say this is one petal and I've got 1, 2, 3 of them, so just multiply by 3. Okay, but we all agree 0 to 2 pi is problematic and you can see why. All right, good. Let's try cosine because it's a wee bit different, okay? Okay, so we're gonna graph r equals 4 cosine 3 theta, and then again, we'll find the area enclosed by one loop and the entire graph. So we can tell right off the bat, all right, this thing has 3 petals. And the first thing I recommend you do is find how long it takes for one petal to get traced out, for one loop to be created. So you set r equal to 0. Notice a is irrelevant in this process. If you want to just ignore it and jump to just setting cosine 3 theta equal to 0, that's cool too. So now we have to think, when is cosine 0? Cosine 0 at pi over 2 plus pi k, where k is an integer. I'm going to use the abbreviation, get you guys used to it. And in this case, remember, we're looking for theta, not 3 theta. So that means if I divide everybody by 3, this is pi over 6 plus pi over 3k. Okay, so at 0, we're not going to have r equaling 0. Pi over 6 is kind of like where it's been shifted. That's where it's going to be 0. But still, every pi over 3, a petal gets traced out. That shouldn't surprise us, you guys, because think about it. We knew there were 3 petals. Just like in the last example, every pi over 3, a petal got traced out. Okay? It's just cosine looks a little bit different. Yeah? Because of the way its period is and where it hits its max and min compared to the graph of sine. So I'll start my table at pi over 6, and then every pi over 3, we're going to get a petal traced out. Halfway is where the max is going to be. So I'm not going to list as many values this time. Watch how we do it. R equals 4 cosine 3 theta. So I'll start with pi over 6. If you want to start with 0, that's cool. I just want to start with where the petal is actually at 0. So I'm going to put pi over 6. Now, If I add pi over 3 to pi over 6, that gets me to pi over 2. But halfway between is where the max is going to be. So like pi over 6, pi over 2, I'm adding pi over 3. If I add another pi over 3, I'm going to be at 5 pi over 6. And if I add another pi over 3, I'm at 7 pi over 6. So these are where all the r's are going to be 0. You can verify if you want. Halfway between is where the petal is going to be at a max. So how do I figure out halfway between? Well, if every pi over 3 a petal gets traced out, half of that is pi over 6. So keep adding pi over 6 to these values, okay, to get the halfers. So pi over 6 plus pi over 6, that's 2 pi over 6, aka pi over 3. And then pi over 2 plus pi over 6 is going to be 4 pi over 6, so 2 pi over 3. 5 pi over 6 plus pi over 6 is just pi, okay? Now, we do have to check though whether they're positive or negative values, so let's see. So pi over 3, 4 times cosine of 3 times pi over 3, that's 4 times cosine of pi. Cosine of pi is -1, so this is -4. And then 2 pi over 3, let's see, that's going to be 4 times cosine 2 pi. So 4 times 1, positive 4. And then this is 4 times cosine 3 pi, -4. Very good. Okay, so now let's come through and label here what we got going on. So pi over 6, pi over 3. Notice we didn't need to mess with pi over 4 in this one, so that's fine. Pi over 2, here's 2 pi over 3, 5 pi over 6, pi, 7 pi over 6, okay? So pi over 6 is at 0. Maybe to hold yourself accountable, the petal's going to live between pi over 6 and pi over 2. If you want to draw lines where the zeros are. 5 pi over 6 and 7 pi over 6. Okay. Good. Okay. At pi over 3, it's -4. Pi over 3, you're going to come this way to -4. Boom. Ooh. 1, 2, 3, 4. And then pi over 2, you're back to 0. Pi over 2, you're back to 0. Okay. So this one went from here. Here was the max. And here. So technically this is also bounding it, if that's a little weird to see, because it reflected, right? So it's going to live in here. Here's one petal. I'll repeat that again. So pi over 6 bounded it. So did pi over 2. Since we had a negative r though, just carry those through, carry this through. This petal has to live in here. Okay. Next one, 2 pi over 3, we have 4. 2 pi over 3, 1, 2, 3, 4. And then at 5 pi over 6, you're back to 0. This one's easy, pi over 2 to 5 pi over 6. This petal's in here. Okay, if it's bothering you, you want to know what this is. You want to knock yourself out. Go add more to your table. And then lastly, at pi, we have -4. 1, 2, 3, 4. Okay, and then since it was negative, then that means it's bounded, right, between, here's 7 pi over 6 coming through to the other side, and then here's 5 pi over 6 coming through to the other side, here-ish. So that petal needs to live right in here. Okay. Boom, there's your 3 petals. Okay, notice this is pi over 3 here. From here to here is another pi over 3. You could also think of this as negative pi over 6 if you like. Yeah, good. And then there's pi over 3. Beautiful, beautiful. Okay, so that's the graph. Now, what if you need to find the area, right? If you're a calculus student. So one petal, I would say the nicest petal to go for is this one. But your limits of integration have to make sense. You can't say this is 7 pi over 6 to pi over 6. you have to read it so that it makes sense when you're tracing it out counterclockwise. So I'm going to say one petal, the area is going to be 1/2 integral negative pi over 6 to pi over 6 r squared d theta, so 4 cosine 3 theta squared d theta. And then yes, it's symmetric with respect to the x-axis, so we can just double it, 2 times 1/2, and then go 0 to pi over 6, 4 cosine 3 theta squared d theta. Good? Okay, then these cancel out. Then this is going to be 16 integral 0 to pi over 6 cosine squared 3 theta d theta. Again, cosine squared, we're going to replace it with 1/2, 1 plus cosine 6 theta. So let me take the 1/2 outside. 0 to pi over 6, 1 plus cosine 6 theta d theta. Are we good? So that's 8. Let's take the antiderivative. Theta plus 1/6 sine 6 theta, 0 to pi over 6. And then this comes out to 4 pi over 3. Okay, perfect. That's for one petal. If they wanted the entire graph, I wouldn't even mess with doing an integral. Again, I would just say it's 4 pi over 3 times 3, so 4 pi. Good? Okay. Moving on, example 3, I think it's the spiciest one of the video. R equals 3 sine 5 theta. Woo! So, we know we have 5 petals. How long does it take for a petal to get traced out? Well, you set 3 sine 5 theta equal to 0. So that means sine 5 theta is 0. That means, let's think, sine is 0 at 0 plus pi k. K is an integer. You don't need to put 0 plus anything, right? So theta is going to be pi over 5k. So every pi over 5, a petal gets traced out. Halfway between, the petal is going to be at the max, okay? So let's list out the values on our table that we're going to want to substitute in for theta, and then r, which is 3 sine 5 theta. Okay, I think sine is easier to deal with than cosine, because at 0, it's 0. You know what I mean? So we've got 0, pi over 5, 2 pi over 5, 3 pi over 5, 4 pi over 5, and then 5 pi over 5, which is pi. Halfway between is where the petal's going to be at its max length. So every pi over 10. So let me put that in. So pi over 10, and then just keep adding pi over 5 in between these, right? You want the halfway point for each of these, which are all pi over 5 apart. So this would be, just keep adding 2 pi over 10. So this is 3 pi over 10, 5 pi over 10, which is pi over 2, 7 pi over 10, you got it, and 9 pi over 10. Okay, it's going to be tricky to graph because these are so small, you know. Ugh, I don't love it, but here we go. And someone specifically mentioned they needed to do 5 petals for their calculus class, so we're doing it. Would I put something like that on a test? Probably not. Here's pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3. Let me just do the big ones. Pi, 3 pi over 2. Okay, so let's start trying to fill in where everything would be. Let's do the pi over 5s first, okay? So 0, we got it. 0's here. Pi over 5. So a little bit bigger than pi over 6. Pi over 5 it's 36 degrees, but pretend you don't have a calculator, right? So pi over 5 is going to be, let me do a different color and let me make it just a wee bit thinner. Okay. 36 degrees. I'll say it's here. And I'm going to go all the way through to the other side. So that's our pi over 5 line. Okay. And then 2 pi over 5. So that's about, it would be 72 degrees. 72 degrees. So where would that be? Maybe like here-ish. Okay. 2 pi. Let me do it in a different color so you can see it. 2 pi over 5. And let me put, this is pi over 5 here so you can really see. Then we need 3 pi over 5, so that should be about the same amount of space on the other side. So 36 times 3, that's 108. So 3 pi over 5, let's say here, okay. And then 4 pi over 5, that is 4 pi over 5, 4 times 30, 144 degrees. So 144, yeah, let's put it about here. 4 pi over 5. And then 5 pi over 5 is done. Okay, those are good. Now we need, we need the pi over 10s. This is getting crazy. So pi over 10, that's 18 degrees. And then keep adding 36. Oof, okay. So then this would be 54. And then, well, pi over 2, that's easy. 7 pi over 10, that's 126. And then 9 pi over 10, we can deal with that later. Okay, so let's see here. Halfway, so I'm going to go like this. Pi over 10, if this is pi over 5, pi over 10 should be about halfway, right? Like 18 degrees. Even if you didn't know what it is in degrees, if this is what we're calling pi over 5, it should be halfway between. Let me do it in a different color that we can see. I'm going to just draw a line. I'm living on the edge. This is my pi over 10 line. Okay. Pi over 10. Then I need 3 pi over 10. Okay. 3 pi over 10. So that'll be halfway, just go halfway between all the other ones that we drew, right? So between 0 and pi over 5, halfway is pi over 10. Then between pi over 5 and 2 pi over 5, halfway is 3 pi over 10. So here's pi over 5, here's 2 pi over 5. Halfway is 3 pi over 10. It should be around here. 54 degrees, that makes sense because pi over 3 is 60. Like right around there, guys. Just do halfers. This is 2 pi over 10. No, 3 pi over 10, so we don't forget. Okay, then 5 pi over 10, easy peasy, because it's just pi over 2. We got that guy, okay. Then who do we need next? So that one's taken care of. 3 pi over 5. Halfway between 3 pi over 5 and 4 pi over 5 is 7 pi over 10. So here's 3 pi over 5. Here's 4 pi over 5. Halfway is 7 pi over 10, which is 126 degrees. That makes sense because 2 pi over 3 is 120. So 126 should be around there. Look at us. We're doing great. Okay. That is 7 pi over 10. And then lastly, 9 pi over 10. Where's 9 pi over 10? Halfway between 4 pi over 5 and pi. Halfway between those two. So I'm just going to say maybe like here is 9 pi over 10, okay? And draw it all the way through. Why am I drawing it all the way through? Just in case r comes out negative there. Oh my God, okay. We got it, you guys. We're surviving. All right, here we go. Now let's plug in. So I know all the green ones, that's where r is going to be 0, right? Boom, boom. And then all of the halfway ones, we have to figure out if they're positive or negative 3. So we do have to sit here and plug them in. So this is 3 times sine, 5 times pi over 10, that's pi over 2. So this is just 3. The next one is 3 times sine of 15 pi over 10, which reduces to 3 pi over 2. And sine is -1 there. So this is -3. This will be 3, -3, 3. Okay, so let's go through carefully, graph all these guys, okay? So pi over 10, the radius is 3. Pi over 10, the radius is 1, 2, 3, okay? And then this petal needs to live between 0 and pi over 5. So this petal has to live in between here. No problem. No problem. I don't need more values. Look at me go. Okay, next. This is where it's going to get a little tricky. 3 pi over 10, the radius is -3. Here's 3 pi over 10. You got to come -1, 2, 3 right there. 1, 2, 3. And then this guy's going to live between these two here. Don't go past this. This is the max length of that petal. Okay. Good. Moving on. Pi over 2, it's at 3. Ugh, that's relaxing. 1, 2, 3 right here. And it's got to live between these two guys. Great. I know maybe the setup, the way I do it's chaotic, but then once you graph it, see, it's like it's all coming together beautifully. I'm so proud of us. 7 pi over 10, -3. Here's 7 pi over 10, but go the other way. 1, 2, 3. And then keep it between these guys, right? Don't make it too fat. Don't make it too fat. And then 9 pi over 10, +3. That's right here. 1, 2, 3. Beautiful. And then stay between these guys. Boom. Okay. How was that? That was so hard. Okay. I would feel so bad putting this on a test. Okay. Now, honestly, like you could find the area within the petal and not have to graph this guy, right? Because now that you know, hey, I can figure out every pi over 5, one petal gets traced out, and then at 0 and pi over 5, it's back to 0. You can just set up your integral. You don't need this whole graph. So I don't know, whoever asked for this problem, is your professor actually making you graph all 5 petals? If so, oh me, oh my, but here it is. Okay, if you want the area of one petal, like I said, graph is not essential to finding this part. 1/2 integral 0 to pi over 5, 3 sine 5 theta squared d theta, right? And you would have known to integrate from 0 to pi over 5. Okay, this is going to be 9, right? And let me take that 9 outside. So 9/2 integral 0 to pi over 5 sine squared 5 theta d theta. To integrate sine squared, we use again half angle identity. So 9/2 times 1/2, 0 to pi over 5. This will be 1 minus cosine 10 theta d theta. And then we have, let's see here. Yeah, we're good. 9/4 antiderivative of 1 theta. This will be minus 1/10 sine 10 theta, 0 to pi over 5. And then you can finish it off. Let's see. I said you could finish it off, and then here I am. I'm like, oh no, let's not leave any leaf unturned. That's sine of 2 pi, so 0 minus bunch of zeros. So what is that going to be? 9 pi over 20. That's for one petal. And then the entire graph would be 5 times that. So 5 times 9 pi over 20. This cancels. This is a 4. So 9 pi over 4. Good? Yeah, okay. That looks good. Now, not everything is going to have an odd number of petals. I told you we can do some with an even number. So the only funky thing is, whatever n is in this case, you actually have double that number of petals. So in this case, we have 4 petals. Oh yeah, 4 petals. So again, you want to see how long it takes for a petal to get traced out. Set R equal to 0. So let me think. Sine is 0 at 0 plus pi k. K is an integer. So theta, 0 divided by 2 is still 0. So pi over 2k. So every pi over 2, a petal gets traced out. But if I have 4 petals, it's going to take all the way from 0 to 2 pi for the whole thing to get traced out. This one's going to be fun. It's going to be so relaxing after the other one we did. Okay, so here's theta. Here's r, which is 3 sine 2 theta. So I'll start at 0, and then at every pi over 2, I'll have another 0. So 0, pi over 2. Keep adding pi over 2. Keep adding pi over 2. Keep adding pi over 2. Halfway between is where the petal's going to be at its max. Half of pi over 2 is pi over 4. Halfway in between is going to be 3 pi over 4. Halfway in between is 5 pi over 4. Halfway in between is 6 pi over 4, aka 3 pi over 2. Okay. 0, pi over 4, pi over 2. I'm not labeling the rest because I don't need them in this one. 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4. Good? Okay, I know these guys are all my zeros. And then I do have to plug it in to see whether they're going to be positive or negative 3, right? The other values. So 3 times sine of 2 times pi over 4 is pi over 2. So this will be 3 times 1. That's 3. I'll give you the rest. Negative 3, 3, negative 3. Okay. And then also keep in mind, right, like your petal has to live between all the quadrants pretty much, which is nice. It's trapped between these values. Okay, so at pi over 4, we're at radius 3, 1, 2, 3. And then just make sure you stay in quadrant 1. At 3 pi over 4, we're actually at negative 3. 1, 2, 3. That's fine. That's fine. At 5 pi over 4, we are at 3. 1, 2, 3 here. And then at 3 pi over 2, that's not right. That should be 7 pi over 4. My apologies. Were you screaming at the at your screen? Lost my mind. Okay. 7 pi over 4, negative 3. 1, 2, 3. Do forgive me. You guys, I've been sick for like a whole week. Can you hear it in my voice? I wanted to put this video out last week, but I sounded a mess. And I've been pausing quite a bit because I have to stop and cough every now and then. But hopefully I'm here for the people. I know you guys have exams coming up. So there's the 4 petals. Are they slightly deformed? Absolutely. Okay. Would I accept this on a test? Absolutely. So I don't know. Is your instructor really picky about the shape of your petals? I don't think they could demand more than this. And then if we need the area of 1 petal, if you're pre-calc, skip this part, right? Area of 1 petal, you can see just integrate from 0 to pi over 2. So area is going to be 1/2 integral 0 to pi over 2 r squared d theta. I'm going to do this part quickly because they're all the same pretty much. You'll have 9 over 2 integral 0 to pi over 2 sine squared 2 theta d theta. Then how do we integrate sine squared something in calc? You replace it with the half angle identity. I already put the half outside. Sine is 1 minus cosine, double the argument. And then this is going to be 9 over 4. Antiderivative of 1 is theta. Antiderivative of cosine 4 theta is 1/4 sine 4 theta, evaluated from 0 to pi over 2. And then this will give us 9 pi over 8. Okay? Good. If you want the entire graph, then you just take 9 pi over 8 times 4 petals. So 9 pi over 2. You also could, in this case, integrate from 0 to 2 pi, because remember, it took 0 to 2 pi to trace out the entire graph. Okay, I have one more. Are you excited? 4 petals, this time with cosine. So again, set 2 cosine 2 theta equal to 0. That means cosine 2 theta is 0. So when is cosine 0? Cosine is 0 at pi over 2 plus pi k. K is an integer. So that means theta would be pi over 4 plus pi over 2k. So again, every pi over 2, a petal is traced out. It's just our starting point is pi over 4. That's the first time the radius is 0, not at 0. Okay? So when you're making your table, like if it's out of habit that you like to start with 0, then start with 0. But just know that the radius when you're doing a cosine graph is not going to be 0 there. So like technically, straighten up. Okay, pi over 4 would be the first 0. And then I'm going to keep adding pi over 2. So pi over 4 plus pi over 2 is 3 pi over 4 plus another pi over 2, 5 pi over 4 plus another pi over 2, 7 pi over 4, like that. Okay, and then technically I would go to plus another pi. No, we're done. And then halfway in between is pi over 4. So keep adding pi over 4s to get the halfers. So pi over 2 pi. See how nice? And then 3 pi over 2. And then 2 pi, which is the same as 0. So that's why if you wanted to start with 0, you can. Okay? Good. So I know these are where all the zeros are. Yes? Good. 1, 2, 3, 4. And then let's see what the R values are at the other places. So 2 times cosine of 0, that's 2. 2 times, this is going to be cosine of 2 times pi over 2, that's pi. This will be negative 2. This will give me 2, negative 2, 2. Okay? Then scoot this guy over. 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4. Okay, so at 0, we're at 2. Ooh. Pi over 4, we're at 0. If you want, yeah, let's put lines through where all the zeros are so you know where your petals have to live between here and here, okay? So like this petal here is going to be stuck right in here. So this petal, don't let it get too chunky. At pi, we have radius 2. So he's here. At 3 pi over 2, negative 2. So here's 3 pi over 2, negative 2 would be up here. And then 2 pi, we have 2. Did I miss somebody? Oh, did I not graph pi over 2? Pi over 2, we have negative 2 over here. Okay, there they are. Sorry, I did it out of order. I was excited to get this one done. Okay, so there's your graph. If you want just the area of one petal, then you're going to do 1/2 integral. Now look at the limits of integration for one petal. So don't go 7 pi over 4 to pi over 4. No, that doesn't make sense. You can call this negative pi over 4 to pi over 4 when you set up your integral. It has to read, you know, in counterclockwise order, but also this is a larger number than this one. So you have to call it negative pi over 4 when writing it as limits of integration. Okay, and then r squared d theta. And then obviously, like, don't be mean to yourself. Change this to 0 and double it. So then you just have 2 times 1/2 0 to pi over 4, 4 cosine squared 2 theta d theta. And then from here, it should be run-of-the-mill. We've done a bunch now. This is pi over 2, okay? And then the area of the entire graph would be 4 times pi over 2, which is 2 pi. Okay, so that concludes the video. Honestly, I don't think you should have to do more than 4 or 5 petals. 3, 4, 5. Would they ever make you do... Well, nothing has 6 petals, right? That's impossible. Because if n is even, it's always 2n. So I'm surprised. If you're the person who asked for the 5 petal, is your professor actually making you graph it? That's a lot of work. With no calculator, they said. When they requested, they said no calculator. So I need to know what's going on. I hope you enjoyed the video, though. Give it a thumbs up. And I'm starting to feel better, so I'll make more new content. But I had to take some time off, you know. Protect the health. I love you all so much. If you need any other video lectures, then hop over to the playlists that are on this channel. I have everything organized by course, like Calc 1, Calc 2, Calc 3, etc. And then you can also follow me on Instagram and TikTok, Math with Professor V. I will do my best to have some more new content. I have stuff ready. I just have to sound well enough to come on and record what I'm saying and also think clearly. But this was fun. I hope you guys enjoyed it. I'll be back sooner than later. Bye, guys.